Someone was saying something?
Sir, are there any plans to do in situ experiments over there, like on the surface itself?
To some extent, they are already being done in the older rovers. This one will also be doing some. I don't remember the exact suite of instruments that this one is carrying, but there have been various experiments that have been done in situ on the Martian surface to check for composition of rocks and things like that. That's what all the rovers have been doing so far, right? Because if you can't bring material back, then just taking pictures is okay for your first mission, not for your next N missions. And well, other than that, another important thing, not quite as landmark as landing a rover on Mars, but another important thing that's happening right now is the annual meeting of the Astronomical Society of India is underway. So, in fact, I'm missing some workshops to be here, which is why you will also see that your usual TAs are not attending today either. Um, and some great news for IIT is expected on Sunday. So look out for announcements regarding us and ASI. All right. So any questions from last time?
Sir, so when we image something with the detectors, then does the quality
Mhm.
of image, like how much does it depend on where, like where on the detector the image lies?
Okay, so yes, there is some non-uniformity in a detector, and it is not something quite generic. So, for example, if you are looking at something through a telescope, even by eye, okay, then often objects in the center will appear sharpest, and as you go further and further off axis, the image quality will degrade. If you now look at the detector itself and you decouple the effects of the telescope from the effects of the detector, then what is going to happen is that detectors can have some non-uniformities, but they are not usually as how should I say, large scale as compared to the telescope. So in other words, on an average, if you take say the central 5 by 5 pixel region of a CCDA and something closer to the edge, they will have pretty much similar quality. But if you pick any two random regions or any two random pixels on the detector, they won't be identical. So we have those kind of issues that can actually be taken care of in the detector. Sorry, that can actually happen in the detector. Anything else? Anyone else?
Sir, when is the mid-sem scheduled?
Our midsem, I think, is on the last day or something, right? You people will have the schedule.
Last day,
Yes,
so
sir.
3rd
2
March,
March,
last slot.
5:30 p.m.
Yeah, so
Okay.
that will stick to the formal slot, whatever it is.
Okay. Okay, so 3rd March it will be exam, right? Okay, thank you, sir.
Yeah. Yeah. So speaking of exam, that poll that I have posted on general is the most one-sided poll ever. I should have probably added a few riders in that. Let's postpone the result, lecture, and all of you will pay me 10,000 rupees each or something like that. Fir bhi log anything for a no looks like the nature of that poll. Okay, so no lecture on Tuesday. We'll wait for others to respond. As I said, respond by tonight. But otherwise, what we'll do is that we won't have the data analysis lecture on Tuesday. I'm 100% sure you all are already working very hard on whatever subjects you are studying. So you won't really need the last night to prep for stuff, right? But just in case you have left some preparations to be done for the last night, then we'll keep that Tuesday free. We will have to take this as an extra lecture after midsem, however. So we'll fix a time slot for it, some convenient time, and then we will have this hands-on data analysis lecture. At that time, we will also recommend some software that you should have installed on your laptops, in particular DS9, most likely aperture photometry tool. These are all cross-platform things. So whether you're using Linux, Windows, Mac, these software should work. And then the TAs will be taking that session and they'll show you how these software are to be used in order to analyze GIT data. And then the last point that I want to make before we get into today's problem solving is that if your group has decided what it is that you want to observe, okay, if you have a fair idea of your target and so on, now is a very good time to message me or the TAs, and we will look at your target, will either approve it or help you find another one which meets all of your requirements. And then while you all are busy doing your midsems, we can actually start acquiring data for you. Okay, so if you know already what it is that you're looking for, then this would be a good time to ping us about it. All right, so let me switch off the AC, which some random dude actually switched on from outside the office without asking me. And on that note, let's start with today's problem solving sessions, which are going to completely focus on data analysis. So here we go. Okay, so in coordinate systems, as I told you, the main thing that we begin with or need to remember is the basics of spherical trigonometry, and you have to find the correct spherical triangle and everything else follows. Okay, so but before we go into spherical trigonometry, let's start with something even more basic. Okay, what are the coordinates of the sun today? Okay, so the question that I'm phrasing is, what are coordinates of the sun today? How would you go about answering this? Okay, nobody has any idea. Fine. What happens? What is this north and south motion of the sun? What is the range of space in which the sun goes north and south because during seasons and so on?
Plus minus 23 degrees.
Right. So to remind everyone, we have the plane of Earth's orbit, and the Earth's axis makes an angle of 23.5 degrees from the vertical, which means that when the Earth is like this and the sun is here, then I have the sun at plus 23.5 degrees declination. And give me one moment. Yeah, sorry about that. Some random AC repair guy keeps coming and switching on AC in my office, royally ignoring the do not disturb sign put outside. Okay, so we were talking about the sun being here, Earth. When the Earth is in this position, the sun, this is the Earth's equator going like this. So this is the Earth's equator now. So the sun is 23.5 degrees above the equator. 3 months later, when the Earth is here, the sun is actually in the plane of the equator. 3 months later, winter solstice, the sun is at minus 23.5 degrees. And then over here, I showed it the other way around. Yeah, no, sorry. This is the equator again, so minus 23.5 degrees. And then 3 months later, when we are here, it is back on the equator. Okay, so on the solstices, so summer solstice, delta is plus 23.5. Then on the winter solstice, it is equal to minus 23.5. And on the two equinoxes, what are the dates of the equinoxes and solstices? When is the sun?
23rd September, 23rd December, and March.
Right. So you can discuss whether it is 21 or 22 or 23. Usually people talk about 21st. So we'll call it 21st. These actually do change a little bit from year to year. Okay. We had all the answers. So summer solstice is 23rd of what month? This is going to be
21st June.
Right. Then winter solstice is 21st December. And then within the equinoxes, the vernal equinox, and what's the other one called?
Autumnal.
Right. So vernal is the spring equinox, which is on the 21st of March, and this is on 21st of September. Okay. Now that means we have our basic declination here, but what about right ascension? Okay, so how did we define the vernal equinox? Does anyone remember this? Or what did we, that's the wrong question. What did we define using the vernal equinox?
RA
Zero,
zero.
right?
Correct. So at this point we had defined RA equal to 0. Okay, so this means that I can add a second column here for alpha, and that is too narrow a column. So this is 0 degrees. Where will the sun go next? Will it, so in summer solstice, is the sun going to be at plus 6 hours or minus 6 hours? How would you figure that out?
Plus 6 hours, right? Summer.
Summer means plus 23 degrees, but is it plus 6 or minus 6?
Okay.
Okay, so to do that, we have to try to understand this diagram. Okay, so I am going to start with putting the sun at the center here, and then we'll put Earth here today and Earth here. So let us say that this thing here is the equinox. Okay, so I have the vernal equinox here. The Earth rotates like this and revolves like this. Okay, so this is the direction of motion of Earth. So, and as seen from Earth, okay, the way we have defined the coordinates, ironically, right ascension increases to the left. Okay, so if the sun is here today, okay, suppose today is the vernal equinox, and I have the Earth here. So this direction in the sky is RA equal to 0, which means that this direction down here is RA equal to 90. This direction up here is RA equal to 270. Okay, so 3 months later the Earth will have moved here. Position of the sun, so maybe I should not draw this arrow here. Okay, I will move the arrow here, because as seen from the Earth, the sun is now in this direction towards RA equal to 90. Okay, so what that means is that I have alpha equal to 90 degrees here. Here it will become 180 degrees again, and here it will become 270 degrees. Okay, now this is confusing enough that we should do something to actually verify it. So simple homework for you is to verify this. Okay, so after the class you can just go look this up and you can see if the logic that we have given is right or wrong. Okay, now there is one more way to think of motion of the sun, by the way, which is guided by this diagram. Yes, Himansh, you have a question.
Yes, sir. I'm a bit confused about the RA thing. So RA zero is defined as the vernal equinox point in the sky.
Correct.
And like now, in which direction does the RA increase? When we go west of RA zero or when we go east of RA zero?
Going east.
Okay, okay.
Okay, RA increases to the east. So it is called right. So as I said, RA, right ascension, increases to the left, uh, because we usually look at a point and measure right ascension with respect to that. The word right means that as things are ascending, they are moving more and more to the right. So that nomenclature is a bit confusing, but RA actually increases to the east. So as you are looking up, if you are in the northern hemisphere, you have the pole star to your back, then RA is increasing to your left. Or as seen in this diagram that I have here, RA would actually increase to your left.
Okay, sir.
Okay. So one more way to think of this, by the way, is that the vernal equinox direction, RA equal to 0 direction, was of course defined by the intersection of the Earth's equator with the ecliptic. That's the way we had defined this direction. But in addition to that, there is one more factor which we can actually think about, which is that the motions themselves are actually taking place in the ecliptic plane, right? So this plane that I have here, this is the plane of the Earth's orbit. Okay, so that means that if I actually were to deal with ecliptic coordinates of the sun, then life would be a bit easier. Ecliptic coordinates of the sun. Okay, so does anyone remember the symbols for ecliptic coordinates? Instead of RA deck, what were the names and what were the symbols?
Ecliptic
We had
latitude was
ecliptic
beta, I think.
longitude, correct, and ecliptic longitude, lambda. Okay, so I have ecliptic longitude and ecliptic latitude. So what will the latitude of the sun be? How do we define the plane of the ecliptic? The plane of the ecliptic is the plane of Earth's orbit, and Earth's orbit and the sun are in the same plane. So the sun is always going to be in that plane. So beta of the sun, so we will have our summer solstice here, winter solstice, then we have the vernal equinox and we have the autumnal equinox. Okay, so beta of the sun is always going to be 0. Now, if you actually calculate it with all details, it is not exactly 0 because the solar system is not perfectly planar. So you have to worry about defining things a bit correctly, and this can take very small deviations from 0, but for all practical purposes, it is 0. Now, on the day of the vernal equinox, the sun is actually at the intersection of the ecliptic and the equatorial planes. We had defined this as the point of RA equal to 0, but we had also defined it as lambda equal to 0. Okay, so this 0 degrees applies here as well. And then how will the remaining coordinates go? It's the same story. We look at this diagram and the coordinates are defined in the same manner. So for the summer solstice, we are going to have, just as here we had 90 degrees, we have lambda is about 90, winter solstice is going to be about 270, and this is going to be about 180 degrees. One more trick which we should remember here is that lambda sun is approximately equal to 360 divided by 365.25 into days since vernal equinox. Right? That's a straightforward calculation. Now, I have said days since vernal equinox rather than saying days since the closest equinox or solstice or whatever, because of this confusion that existed earlier, whether all of these really are 21st or some of them should be 22nd, 23rd. So instead of trying to remember all of that, this particular date is something which you can remember, that 21st March is going to be vernal equinox for sure, and then you can just count everything since that. So if I want to calculate the position of the sun today, okay, so let's actually do this calculation now. Okay, so what is, so coords of the sun? What is today's date? Wow, everyone is really sleepy. What is today's date?
19th Feb.
19th Feb.
Okay, 19th Feb. Okay, so first we can ask the ecliptic coordinates. Lambda equal to how much? And then beta we are going to say is 0. So how many days from today till 31st March? Sorry, 21st March. So Feb has 28 days. So 21st Feb to 21st March would be 28 plus 2. So we have delta T is equal to minus 22 days from the vernal equinox. So lambda is going to be 360 minus 22 divided by 365.25. Remember this 0.25, by the way. This is a rough way of accounting for the leap year. The exact value is a bit lower than this, but this is good enough for now. Okay, so 360 minus this into 360. So any doubts about why I am taking this? So what I'm saying is that in 22 days, the sun is going to be at lambda equal to 0. So I can actually forget this part for now. Let's move this out. So in 22 days, lambda is going to be 0, which means right now it is about minus 22, but it is not exactly 1 degree per day. It is 360 divided by 365.25 degrees per day. And by correcting for all of that, it will give you the exact value. So what is this number?
338.
Okay, so anyone else?
Minus 21.68, so 338.
Okay, so that is why we added this 360, because conventionally we have chosen lambda to go from 0 to 360. And that, so when you get a negative answer, you just subtract it from 360. Okay, so that is now the lambda. But now from this, we should try to convert to RA deck. And for that, we need to have spherical trigonometry. Now, this conversion is actually quite straightforward. So what I am going to do is I am not going to solve this here, but this is your homework again. So convert from beta lambda to RA deck. All right. Any questions on this so far? I can even give you the answer if you want. Let me see. Get sun time dot now. Okay, so the sun's coordinate right now are, so alpha is 332.76 degrees, delta is minus 11.22 degrees. Okay, by the way, this agrees with our overall idea, which was expressed at the top here, that in December, on 21st December, the alpha will be 270 and it will slowly increase to 360 as we come to March. And you would expect it to be something around minus 30 degrees or so about a month before 21st March. And that is roughly where we are. This, of course, is not going to be linear because the linear motion is in the ecliptic coordinates, and it's going to be non-linear when we go to our equatorial coordinates. Okay, ready to move to the next thing. Any questions on this calculation so far? All right, so given these coordinates of the sun, now let's try to calculate where will the sun set today. The answer, of course, is west, but what azimuth? Okay, so to solve a problem like this, we have to use spherical trigonometry. So drawing these diagrams is something which you should get comfortable with. So I have my zenith here, north, south, and then I have east and west. The declination of the sun was negative. So the first part I can ask is, will the sun set to the north of west or to the south of west? Anyone?
South of west.
That is correct. So the equator Remember the north celestial pole. Let me change color here. So the north celestial pole is here, which means the equator is actually going like this. But the equator passes through east and west. Okay, so anything which is having a negative declination belongs to the left half of this figure, and that's going to set to the south of west. So the sun is going to set somewhere here. Okay, so let's say this is sunset. I want to calculate the azimuth at sunset, which is this angle. Right? So what about the altitude at sunset? What will be the altitude of the sun when it is setting?
0.
Whatever will be the horizon's altitude.
Correct. Both answers are correct enough. So nominally 0 is the point which is going to be 90 degrees from the zenith. But if I am standing on top of a tall mountain, I can see a bit further down. So the altitude might be slightly negative. If you are in a typical city area, you don't have a clean horizon. You will see the setting behind some distant mountains, or you'll see it setting behind buildings or whatever. So the altitude will not be 0. It might be something positive. But setting nominally would mean that altitude is equal to 0. Now to calculate the azimuth, I have to convert between our angle. So I can't directly convert between RA deck and this, because I don't know what the sidereal time at sunset is going to be, and that becomes a slightly tricky question to solve. But I don't actually need to know all of the information. So let us try to make our basic spherical triangles and see what actually comes out of it. So to create a spherical triangle for doing coordinate convergence, we always have to use 3 points, the 3 vertices of the triangle. One of them is going to be the object itself, and the other 2 are going to be poles of the 2 systems that you are using. So in this case, that is the north celestial pole over here, which is the pole of the equatorial system, or also the HA deck system, the hour angle and declination. And then you have the zenith, which is the pole for the Altaz coordinate system. So I can join these 3 now. This would be one. This is the other line. Right? This is a line that is perpendicular to the equator. This particular line is perpendicular to the horizon. So this is my spherical triangle that I am using. And now I have to mark the angles of this triangle. Okay, so this angle here between the meridian and this point, what is this angle going to be? If the sun were here on the meridian, okay, so that this line would have passed through the zenith, that would have been an hour angle of 0. And the angle that this line in general makes with the meridian is the hour angle. Right, so when I have something rising, my hour angle would have been negative, then it comes overhead, that hour angle is going to be 0, and then as it is setting, hour angle is positive. So this is my hour angle. Notice that it is not actually going to be 6 hours. Hour angle would have been 6 hours for this line, which would have passed through west, or 90 degrees instead of, if you want to think of it in degrees instead of hours. So this is going to be some hour angle that is less than 6 hours. Okay, that's an important factor to remember. Then let us look at the other angles. What is this length from here to here? Anyone? Okay, let's draw another star which makes that a bit easier to imagine. Suppose I have a star here. Okay, and I connect this star to the North Pole. What is that orange arc that I have drawn?
90 minus declination.
Correct. So the sun right now is in a weird spot for this to be a bit counterintuitive, but this angle is the same thing. Right? So what I am going to have here also is 90 minus declination. Remember that the declination over here is negative. So 90 minus declination is actually going to be a positive number greater than 90, which is what you see from the image as well. The equator, which is that dashed red line, is at 90 degrees from the north celestial pole. The sun is below that, so this angle is actually going to be greater than 90. Okay, so we have that angle. This is the angle which we don't care about usually, so we can ignore that. What about this angle? So this angle is the same as this. Okay, so let me use a different color here. So this angle is the same as this angle over here, and that is nothing but 360 minus azimuth. Why? Because this angle here is my azimuth. Agreed? So this is 360 degrees minus azimuth. Okay, then that leaves, so we have defined our angle here, we have defined 90 minus delta. We have decided that we don't care about this angle over here. Then this angle we have marked, so we are left with two more things. One is this angle going from Z to sunset, to the sun which is setting, this one over here. What is this one? When the sun is setting, how many degrees will it be from the? Correct. It will be 90 degrees from the zenith. Okay. So let me actually get rid of those lines and then mark it. Very good. And that leaves us with one last angle, which is the angle between Z and NCP. And that you might remember is 90 degrees minus the latitude, where if I am at the North Pole, then the North Celestial Pole itself will be overhead. So Z to NCP angle will be 0. If I am at the equator, the North Pole is going to be on my horizon. So that angle is now 90. Okay, so we have marked all the angles of our spherical triangle, and we have marked all the sides of our spherical triangle. From this now, the properties that we know, okay, we know 90 minus delta. We know 90 minus latitude, we know 90, 90 is still 90. We want to solve for 360 minus azimuth. We do not know our angle and we do not care about this angle. All right. So based on this now, we have to calculate 360 minus azimuth. What is it? So for this angle, the purple angle, we know the angle opposite to it. Okay. But we do not know any of the other angles. So sine rule is not useful. For the sine rule says sine of A divided by sine of capital A is equal to sine of B divided by sine of capital B, and so on. So I need to know both the opposing values, which I don't know in this particular case. On the other hand, does anyone remember the cosine rule? Can you look it up from older notes?
Cos of small a equals cos small b cos small c plus sine small b sine small c cos capital A.
Okay, so cos b cos c plus sine b sine c cos a. Okay. Now in this particular case, capital A is this. So the vertices are capital letters. So in my case, if I know all of the edges, right? I have ticked off the edges here. It is this one, and this one. So since I know all of the edges, small letters are known, capital A is unknown. So I can actually now substitute this. So I put A is equal to 360 minus azimuth. That makes small a is the angle opposite to that. So that is 90 minus delta. B and C I can choose in any order. One of them is 90 degrees and the other is 90 degrees minus the latitude. Okay, now can you actually simplify this equation on the basis of this? I will give you a minute. So you simply have to substitute these values into this and tell me what is the final relation between. So we will represent the latitude by lambda Mumbai. In this particular case, you are all at different locations, so the azimuth will turn out to be slightly different probably, but let's just solve for this. So I start substituting here. Capital small a is 90 minus delta. So on the left side I have cos of 90 minus delta or sine of delta. Cos b and cos c. Uh, b is 90. What is cos of 90?
0.
0. So the first term disappears. Then I have sine 90, which is 1. Sine c, which is sine of 90 minus latitude. So cos of lambda Mumbai. And then I have cos of, so cos of 360 minus azimuth, what is that equal to? So
Cos of
360
azimuth.
minus azimuth is just same as minus azimuth, and cos of minus x is equal to cos of x. So this is equal to this, right? So this is now your equation that we have. So from this I can actually solve for the azimuth. So let's actually do that. So the latitude of Mumbai, I can tell you, is okay. So lambda Mumbai is 19.13 degrees, and then delta sun, which we had calculated, was up here 11.22 minus 11.22. So from this I now want azimuth. So go ahead and calculate that. I am also going to calculate it. I am making up problems from older problems as we go along. I do not know the final numerical answers. So I'm going to wait for you to tell me the answers. Otherwise, we can all just keep looking at each other's faces. Well, actually, I'm looking at your names instead of faces, but close enough.
101 degrees. 101.8.
Yes, sir.
Okay, so you are getting 101.8. Two people got that. How many more? Keep calculating, and meanwhile, think about your answer and see if it is reasonable.
No, wait, I think it should be 360 minus that.
Okay, why?
Because north to south is 180 degrees. And now it's slightly away from south towards the west. So it has to be greater than 180 degrees, the azimuth.
Okay, so the first answer that you got is that azimuth is equal to cos inverse of something, and then that by default your calculator told you 101.88 degrees, so 101.9 degrees. Does everyone agree up to here? Anyone got an answer other than 101 degrees? And this is the part which I had then warned you about in class, that you have to worry about the sign of this thing. Remember that we are trying to find azimuth between 0 to 360, but the inverse function has a range only of 180 degrees, not 360. So what it is telling you is that it is telling you another point on the sky, namely this one, where the azimuth would have been, where this equation would have been solved. That actually would have been the azimuth of sunrise, by the way. Assuming the declination of the sun does not change through the day. But in practice, what you're looking for really is 360 minus this, which is going to be 258.1 degrees. Right? Is that correct? 258.1 degrees? 360 minus 101?
Yes.
Okay, so this is the answer, final answer. I ran out of space, so I'm writing Teda Meda here. So this is an important part to remember. And if you simply had mugged up this formula, for example, this is a simple enough formula to remember. But what you gained by drawing a diagram like this is the visualization, plus a little bit of common sense intuition plays in here that 90 degrees is due east, 101 degrees sounds more like east than west. The sun cannot actually set in the west, in the east. We need the sun to set in the west for nature to continue making sense. Okay. Any questions about this problem so far?
So like I was thinking of one method to find the expression for delta on any day. So like since it's supposed to be periodic and so assume it's going to be sinusoidal. So take a function something like a sine bt plus some phase and then use the boundary conditions that at equinox it should be 0 and
So it turns out it is not exactly sinusoidal. Okay, but you can calculate it from this equation. Okay, so what you have is a similar set of spherical trigonometry equations that you have to solve. Okay, where lambda is linear with time, but alpha and delta are not linearly related to lambda. Okay, so alpha is a non-linear function of lambda, delta also becomes a non-linear function of lambda. You can actually convert it, and it turns out to be like before, there is going to be a sine inverse of sine something divided by cos something. That 23.5 degree angle is going to play a role here. Okay, so what you are saying is right, it is a periodic function, but periodic does not mean sinusoidal. So it will be sinusoidal to 0th order, but the exact expression will be something different. All right, so let's do something else. Okay, there is a project that I've been toying around with, which might be fun to do with all of us in class. So let us imagine that we actually have the moon over here. Okay, and we have two observers standing at different points on Earth. So all of you are in your hometowns. So let me ask, how many of you are in the northern part of the country? Can you name some cities where you are currently based? Anyone? Oh, nobody is attending from north. Okay, western part of the country. I am in Mumbai, so I'll note that down.
Pune.
Okay. Okay, so Mumbai, Pune. I am looking for the westernmost point. What about east? Anyone from northeast?
I'm in Kolkata, so not northeast, but still towards.
Okay. Someone else had unmuted. Okay, what about south?
So I'm from Hyderabad.
Okay.
So we can clue in Vedant over here. He's probably the southernmost.
Probably yes. So okay, but in general now, does anyone remember? So I'm quite sure we'll have someone sitting in Delhi as well, if not further north. Hopefully we have people further north, south, east, west. We have not yet spanned the country really. So anyone know roughly what the dimensions of India are? Order of magnitude? What's the north-south distance? What's the east-west distance?
4,000 kilometers.
A bit less. It's some 3,000, 3,500 kind of thing. Okay, so but since we may not have people at ekdam extreme corners of the country, let's actually take our D. Okay, so D will be approximately 3,000 kilometers. Okay, so on the basis of this now, I have a few questions that we can try to solve. Okay, so the first thing is, what is the distance to the moon itself? Any idea?
3 into 10 raised to 5 kilometers.
More than that. Okay,
Three
so the way to remember this is in easier units. So it's about 1.3 light seconds. 1.3 is a easier number to remember, and 1 light second is the distance traveled by light in 1 second. So that's 3 into 10 raised to 10 centimeters or 3 into 10 raised to 5 kilometers. So that into 1.3 means that the distance from moon to earth is about 4 into 10 raised to 5 kilometers. Okay, so if we have two observers who are separated by 3000 kilometers and we two people look at the moon at the same time, what's the parallax going to be? That is my question. Solve. Did everyone understand the question? I have two observers standing at two different points on Earth, separated by about 3000 kilometers. I have the moon over here. One person sees the moon in this direction, the other sees the moon in this direction. What is roughly the angle between the two? So that is simply we are constructing a triangle like this. And for simplicity, we can just put the moon overhead for one observer. This is 4 into 10 raised to 10 centimeters. Or we can use kilometers here, 4 into 10 raised to 5 km. This is the moon. This is observer 1, observer 2. This is 3000 km. So this angle theta is how much?
0.4 degrees.
Okay, so anyone else got this answer? I am getting a much smaller answer here.
I'm getting 3.75 to 10 to the power minus 3. So
okay, so everyone is getting very different answers. So we need to figure out what is going on. No one?
I'm getting 6.5 into 10 to the power minus 5.
Okay, so everyone is getting very different answers. What do you think might be going on here? So first is for those using calculators, make sure your calculator is in degrees mode, not in radians. Okay. The second thing is that make sure you are all using consistent approximations. Here I have made this angle 90 degrees, which means simply theta is equal to tan inverse of 3000 kilometers divided by 400,000 kilometers. That is the last part. You have to make sure that your units are same. If one of them was in kilometers, the other should not be in meters. Make sure they are in the same units, because the thing inside the bracket here has to finally become dimensionless. Okay, and when you do that, you do get 0.43 degrees. Or if you want to talk about it in terms of arc minutes, that is about 25.8 arc minutes. Okay, does anyone know what the size of the moon itself is? Angular size of the moon?
half a degree.
0.5 degree.
So what it means is that if two observers looked at the moon at the same time, okay, then they would actually see the moon separated by almost as much as the full size of the moon itself. And this is actually the good chance to use our current geographic distribution to actually measure the distance to the moon. But before we get to that, there has to be one more part which we have to worry about, which is how fast does the moon move? Any idea? So this has to do with angular speed. So this brings us to a related question. See, when we talked about the sidereal day and the normal solar day, we remembered that the Earth actually has to turn extra in order to complete to point to the sun again, right? We have to turn about a degree extra. That's why the solar day is about 4 minutes longer. Stars rise about 4 minutes earlier every day. In case of the moon, something actually even more odd happens. So I have the sun, I have the earth over here, and I have the moon going around the earth in this direction. So suppose I start with the moon being here and I move And as the moon comes back, the earth has actually moved forward quite a bit. Okay, the earth has actually moved forward. This takes an order of a month. So the earth has moved almost 30 degrees. And to go from new moon to new moon again, the moon has to move that much extra distance. But if I'm calculating angular speed of the moon, I want to calculate it with respect to the stars, right? That's the angle. The stars are my absolute frame. That is the angle that the moon is covering. To put it another way, between one full moon to another full moon, or between one new moon to another new moon, Amavas to Amavas, the moon has not gone around 360 degrees. It has gone around more than 360 degrees because the earth actually moved in that duration. So it would have covered something closer to 390 degrees or so. So the period of the moon, which we remember, 1 month, 29 and a half days, as it turns out, is not the actual revolution period of the moon. The revolution period is actually 27.3 days. This is a number out of my memory, so I'm marking it with a star. Someone please go and check that this number is actually correct. Now to calculate the angular velocity of the moon, okay, I could directly do v by or 2 pi r by p, right? So I can do 2 pi degrees divided by the period, and that will give me the degrees per minute that the moon moves. But is this going to be the speed at which the moon moves with respect to me? Or is there something else that I have to worry about?
Our own motion.
Right. So there are two factors that we have to worry about. The first is that as we are standing on Earth, we are moving with respect to the center of. So this formula that I have here, sorry, 2 pi degrees likha hai maine. This should have been 2 pi radians. Okay, the speed that I am talking about is with respect to the center of the Earth, but I am not on the center of the Earth. So for example, imagine something going around the Earth like this. Okay, so if something is orbiting very close to the surface, then to me, even if it takes exactly the same amount of time to go around the Earth, to me it will whiz past me very, very fast, because because the separation between me and that object, remember omega is actually v by r, and whatever v, if it is close to me, then locally it will appear to move very fast. So our separation, the fact that we are not at the center of the earth is one problem, and the fact that we are also rotating because of the earth's motion, we have our own velocity. So for a correct calculation, we have to correct for all of that. So I will simply mark here that this is approximate. Okay, so approximately the degrees per minute we can. So in the interest of time, for simplicity, let us actually calculate this. So can you tell me how many degrees the moon moves per minute? So 360 degrees in 27.3 days, and each day has how many minutes? 24 hours of 60 minutes each. So the omega of the moon is
around 0.5 arc minute per minute.
okay. Let me check this in arc minutes. Yeah. Okay. So which means that suppose I take a picture right now and you take a picture 10 minutes later, the moon itself is going to have moved with respect to background stars. So it is important that we actually take these. So the way we can actually measure the distance to the moon is that your cell phone cameras these days are actually good enough that you can actually see stars in the pictures quite easily. What you need to do is you need to take a picture that has the moon and some stars. Now the moon is a very bright object, which means that it will often saturate in your cameras and you won't be able to measure the position of the moon very exactly. So in order to take care of that, you have to observe it when the moon is a crescent. So just a few days after the new moon. That could have been, for example, early this week. But instead of that, we can repeat this exercise next month if people are interested. So few days after the new moon, we fix a time and everyone images the moon at the same time. The sky has to be dark enough, the moon has to be a crescent so that it is faint enough, stars have to be visible. And by doing all of that and combining it with known distances between the cities, we can actually calculate the distance to the moon. Just an interesting exercise to carry out. Okay. Any questions about parallax? I thought instead of talking about parallax of stars every time, we can talk about parallax of the moon, closer to home object.
Sir, this 27.3 days is the sidereal period of the moon, right?
Correct. Yes. So 27.3 days is the time that the moon takes to actually complete 360 degrees around the Earth. When we are talking about going around the sun, it has to spend that extra time moving those extra 30 degrees. Any other questions? Yeah, I just realized I've been saying 30 degrees. It's not 30 degrees. It is 360 divided by 30, which will be about 12 degrees. So the moon has to move extra 12 degrees, which will take around 1.5 days or so. Okay. Want to do one more problem?
Sir, it won't be like
Yes.
that, no? Like the extra distance that the moon has to move will basically just be how much Earth has rotated itself, no?
How much the Earth has revolved in that duration, not rotated.
Yeah,
Right.
sorry.
So moon would have moved 360 degrees in 27.3 days. Okay, in 27.3 days in the same time. So Earth would have moved by how much? About 27 degrees, right? So now moon has to move extra by this much amount at the speed of 360 degrees per 27.3 days. So the extra amount that has to be moved now, how much time is it going to take? So it's 27 into 27.3 divided by 360. But in this duration, so this is days. But in this duration, the Earth will have moved a little bit more. So you have to solve it convergently, and the answer comes to be about, so that is called the synodic period. Okay, so that is the period as measured with respect to the Earth Sun system. As this thing is called the sidereal period. So that is period measured with respect to stars. Whereas this one is with respect to the sun. Okay, and this is about 29.5 days if I remember correctly. I will again put a star there, which means you have to verify this. All right. Want to dive into a more complex problem now, or you have any other doubts and stuff that you would like to discuss? Any questions, anyone? Okay, so let's go to that sunset problem again. Okay, we calculated the azimuth of sunset. So azimuth of sunset is equal to, क्या था formula? This was cos inverse. अरे अभी किया यार 2 pages पहले.
Sine delta by cos azimuth. No, not cos. Right.
Okay, so this was the formula that we had. And then a related question was, how are things changing? How are the longitude, latitude related to ecliptic coordinates? How are they related to altas and so on? But here we are looking only at delta. Okay, so now the question is, how is this changing? How does this change with time? Oh. Okay, how does this change every day? How would you calculate it? So for that, we would have to go here again. Okay, we start from here. We say that the ecliptic longitude is changing roughly at this rate. Then from the ecliptic longitude, we went ahead and calculated the declination in a formula that I did not derive here. By the way, the reason for not deriving this formula is that you'll find it worked out in a lot of places in your textbook, a lot of online places and so on. Okay. So you would have to now calculate delta from the sun's ecliptic latitude and ecliptic longitude which was always 0. And then from that we use this formula to actually calculate uh, the azimuth. Okay. So after doing all of this, what we are doing essentially is that we are converting. So we get azimuth, we get from delta. The delta itself we got from lambda comma beta, but beta is always equal to 0. So we can ignore that. So we got delta. My arrows are pointing the wrong way. I should have them pointing here. And lambda itself was a function of time. So if I want to calculate dA by dt, then that is simply going to be an exercise in the chain rule. Right? d lambda by dt is a constant. So this part is easy. How about calculating this? Can you differentiate this equation and tell me what dA by d delta is going to be? Anyone? Derivatives याद है या भूल गए सब लोग? What is the derivative of cos inverse?
1 by square root of 1 minus x square.
Yeah, there is a minus sign also. Okay, so can you now, and then the derivative of sine?
Cos.
Yeah, so लगाओ chain rule. dA by d delta is going to be what?
Minus cos delta upon square root of cos square lambda minus sine square delta.
Yeah, so that takes care of the first part, but inside that I have sine delta. So I have to differentiate that also. Which gives you another cos delta. Yeah, I might be wrong about the minus sign, this part I had made notes of in a hurry. So I might be wrong about the minus sign, but again, can someone please cross check this? For a change, I will be okay with you looking stuff up while we are in the lecture.
Yes, sir.
Okay,
Positive
so
comes in the sine inverse. Cos inverse has minus.
okay. So here I am going to be left with minus cos lambda Mumbai divided by square root of cos square lambda Mumbai minus sine square delta, and all of that multiplied by the second term, which is derivative of cos delta, sorry, derivative of sine delta, which gives you cos delta, and then you have that cos lambda Mumbai left there anyway, which will cancel out this part. So this is your final answer. Anyone got a different answer than this? I will interpret that silence as a no. This was simply equal to omega. So now I'll give you the third part which we need, which is this d delta by dt. We have not solved that part. Sorry, not dt. This was d lambda. We have not solved that part, but I'll tell you the answer. This answer is sine epsilon cos lambda. Note that there are two lambdas here. This lambda that I am talking about is ecliptic longitude, whereas this lambda m that I am talking about here is latitude. Sorry, this is latitude of Mumbai of the observer. Okay, so that gives us our final formula, which is that your dA dt is, so as I said, this is something I have done before, so I have the answer which I'm going to write directly. This is cos delta sine epsilon cos lambda divided by square root of cos square lambda Mumbai minus sine square delta. Okay. What does this tell
So
you?
what is epsilon?
Epsilon, good point. This is 23.5 degrees. And it is called obliquity of the ecliptic. Okay, so just as you have your latitude coming in between your alt-as to HADEC conversion, similarly to go from equatorial to ecliptic system, you are going to have that angle coming in, which is 23.5 degrees. That is usually denoted by epsilon. Okay, so this tells you a bunch of things. First let me start with a caution, which is that although we have done this as a continuous differentiation, uh, in order to get the azimuth, we had assumed that altitude is equal to 0. So this is valid only at sunset. Okay, sunsets and nowhere else. And that's the important part to remember, because to get capital A, we had said small a equal to 0. So you cannot say that this is the rate at which the sun goes across the sky, for instance. That is also a rate of change of azimuth, but that will not be calculated through this mechanism. The second is that if when we split this into these three terms here on the right, okay, when I told you to calculate azimuth from declination, that problem was doable. It was non-trivial, but it wasn't a nightmare. Okay, and that is this calculation that we did. Okay, similarly, the middle calculation, which has to do with conversion of array into ecliptic coordinates and vice versa, by itself is a doable thing. And d lambda by dt constant is also something we had solved. So taking three tractable problems and sticking them together, we could solve what otherwise would have been a very, very complicated problem. And the last part is that this goes back to the question which I forget who had asked, which is whether we can approximate the motion as a sinusoid. If it was simply a sinusoid, then this derivative on the right would have just been a simple cosine kind of function or a sine kind of function as well, right? So it is this lambdas and epsilons, lambda m and epsilon, which refuse to disappear from this equation, which is what is giving us agony. Okay, so it shows some kind of a periodic motion. At first approximation, it may even appear like a sine wave, but isn't exactly a sine wave. Okay, so I've walked through or run through a long problem here, but I really would like you to do two things specifically here. First is that the homework problem that I mentioned in between, which is you convert this array deck into lambda and beta, you should solve this homework problem. The second is actually try and walk through the answer that we calculated here. Get familiar with how to draw these kind of diagrams and how to get spherical triangles, because that kind of imagination and intuition is going to be important for you. And the third thing, I said two, but okay, cheat kiya, is that actually walk through all the problems that we did here. Okay, make sure that you're following what is going on. If you directly try to solve these problems without having gone through some kind of practice like these tutorials that we are having right now, then you might find it much harder to solve it. Okay, in especially in an exam kind of scenario. All right, so I will end with that actually, though we have 15 minutes left. The results of the poll still seem to strongly indicate that we are not going to. Oh, there are some yeses now. There are 3 yeses and 16 nos. But that is still strongly in favor of not having a lecture on Tuesday. Anyone who has doubts before midsem can of course post them. I would strongly encourage asking on general or sorry, on the discussions channel rather than general, so that general doesn't get cluttered up. And asking a question there instead of a private message means that others in class will benefit from the answer. Maybe someone else can give you the answer. TAs can also answer instead of me. So that would be the best way to go. So, since we are likely not meeting before midsem, I think instead of diving into yet another problem, let us stop here and open the floor for questions and discussion.
Sir, shouldn't there be omega factor also in the final expression of dA by dt?
Should there be an omega factor? No, because, oh, sorry, yes. I was going to say in the final answer there won't be, but in the equation there will be. Yes, there is omega here. You are absolutely
And sir, the
right.
minus sign?
The minus sign in my derivation seems to have disappeared somewhere. So we might have messed up a minus sign somewhere and I have forgotten about it. I will recheck this and you should too. Any other questions? Few other points, by the way. I will try to mark up over this weekend which are the must-read parts of Moodle and which are the good-to-read parts of Moodle. Many of them you should also have the discretion of being able to figure out by yourself what were the details covered in class. Usually stuff that is covered in class is self-contained. You should not have to refer to any formulae or anything outside unless I've explicitly assigned it as homework. Also in the exams, I will give you a set of formulae and constants and everything that you're likely to require. So don't worry about that. The midsem will be on, I presume most of your midsems by now are happening on Code Tantra. That's at least what the physics department has adopted. So we will have that standard setup where we will have remote proctoring, video proctoring, and you will give your exam on paper and pencil, upload answers by taking photos in the SAFE app. So that's how the midsem is going to be. How many of you have not used this kind of setup before? SAFE plus Code Tantra. Anyone?
Sir, actually, like us third year EP students, I don't think we have had any exam in Code Tantra till now.
Okay, so let's see. If you have not had, so how many non-EP people have not used this setup up to now? Everyone first lower your hands and then let me ask this again. Okay, so there are a few more. So what we should do is two things. First is that the EP Janta should have your CR talk to the department and organize a practice session, a demo session. And then maybe on Tuesday in our regular lecture slot, we will just hold a small orientation session to give you an idea of what the midsem is going to be like. Okay, so next Tuesday we will hold a small, this coming Tuesday we'll hold a small demo for what the exams will be like. Yes, Bhavini.
Sir, for MEC, actually there was a mock session using Code Tantra for one of our quizzes, and it actually did not work out at all. Some of the people were not able to see the paper, and I was one of them. So, is there any way
Okay,
of
so
like,
the paper is not going to be on Code Tantra. The paper will actually be on the SAFE app.
Right. Okay. And
so the idea is that you use, okay, so the for those of you who have not heard of this before, the idea of full view proctoring is roughly like this. You actually use two devices. So I have one device which is something like my laptop set up here at some distance from me, and then I have to sit at a distance so that not even possible within my office table apparently. Okay, maybe this works better. Yeah. Okay, so and you will have in front of you only your mobile phone, ironically, and you will have blank sheets. Okay, so you are sitting with some sheets here. The paper will be visible on your phone in the Safe app. Safe app is designed by one of the IIT Bombay faculty members, and that app makes sure that everything else in your phone is locked up in that time. So you'll see the questions on this. You are allowed to use paper, pencil, calculator, whatever to solve the questions here. And when you are done, you take a picture with that app again and upload it. Okay, and this app is designed to be robust to network failures and so on. So even if you have a power cut in between, your internet stops working or whatever, the quiz can continue. What we do with the laptop camera is that you will have invigilators. So each of you will be assigned to a room, and there will be 8 to 10 students per room. Each room will have an invigilator who will make sure that कोई पीछे से आके कुछ कर नहीं रहा है. So the setup has to be such that at all times I have to be able to see your face, both hands, and the papers that you are writing on. So the setup which I am showing you right now is actually not optimal, because what I can do is I can have secret sheets coming in and out. I could have a formula sheet that is sitting here which I bring in and so on. So what you have to do is your tabletop, your hands, face have to be visible at all times during the exam. Also, it will be a 2-hour paper, so you are not actually allowed to take a break in that time. So you want to get a bottle of water, you get it, but beach mein uthna nahi hai, kuch nahi karna. That's how the setup will be. So that is called a full view proctoring examination, and we've been doing it in the physics department. We have been running your entire 107, 108 courses like that right now. So physics department is used to doing this on a massive scale, 1400 students, 140 proctors actually making sure that nobody is cheating and so on. So we have significant experience with that, and we'll put that to use for your exams as well.
Yes, sir. So
Any
we
questions
will
about it? Yeah.
ask our CR for contacting the department
Yeah, so,
authorities.
but anyway, we will also do a demo on Tuesday in our regular lectures.
Thing is, we don't even know what are we supposed to do, as in how are we supposed to register and how are we supposed to log in.
Correct. So they will, that's why they will send you all the details. Otherwise, I will send you those instructions beforehand.
Okay, sir.
Okay. So yeah, I know it is new and it probably will take some time to get used to, but the basic idea remains. Okay. See, you have to realize this, that most of you will not try to cheat at all. Okay, this, as I have highlighted before, this is an elective. You are all really here because you want to learn astrophysics. Okay, and there's opportunity to drop the course. I am not enforcing lecture attendance, nothing. So you are doing this out of interest, and exam is just one of the things that you do as a part of the course. There should really be no reason to cheat. But there are two factors we have to consider. One is that some people will still want to cheat, and for them cheating is trivial. Second is that given that others might be cheating, more people get tempted to cheat, and which is why we have to do all of this full view proctoring and all this business. Although I really am not very fond of these ideas, because I think ideally we should just have honor code and everything should be based on that honor code. But given that that is not currently how things are going, we can't proceed like that either. So then the question is, okay, why not just set an exam on your laptop? Because then it's very easy for you to have maybe a second monitor attached. You have something that is visible on that. If you are working on your laptop, it's very easy to cheat. Okay, and you are IITians. If I give you a challenge key, okay, here is a system which I think you can't break, then it will take about 5 minutes for you to break that system. I know loopholes in the code tantra plus safe system also. There, some of them are easy to implement, some of them are hard. The easiest ones we have patched, but I'm really not interested in this cat and mouse games. But what we want to make sure is basic sanity in how the exam is being conducted, so that you can at least feel sure that no one else is blatantly cheating. The other option, if the mid-sem experience turns out to be horrible for everyone, then for end-sem we'll switch to open book exam kind of thing instead. So what we'll do is, just like you have the graded assignments, I'll give you end-sem which is open-ended. We'll give you, I heard feedback that you would like to have a weekend included in that, so I'll give you good enough time for the end-sem. We can switch to that as well. But for midsem, we'll try to do it. Also just a 20-mark exam. It's not a lot of weight. So we are going to try to do the usual thing that the department has been doing. Okay, and so the purpose of, so you need two devices, keep that in mind. You need either two phones or phone plus laptop or something like that. One device is our eyes on you. This is to compensate for the fact that invigilators can't be walking around and seeing if you are reading from something else. And the second device is what will actually allow you to solve the paper and upload it.
Sir,
yes,
about the project, so what is the procedure that we are going to follow now? As in, do we have to prepare some kind of a document in which?
No. Writing things down is anyway useful, but right now, so for the immediate phase, which is to acquire data, you actually don't have to create any formal document, but instead of just telling numbers on the phone or on Teams, it will still be useful if you write them down so that there is no chance of miscommunication. But what you have to do now is you have to say, okay, I want to study. I'll keep using eclipsing binaries as my example, since you are not allowed to do that. So I want to study this particular eclipsing binary. Its period is so and so. Can you please give me 10 data points spread over the next 4 days? What we will then do is we will go and verify what the visibility over the next 4 days is actually going to be like. Do we have that phase lock kind of problem that I had discussed in one of the classes, where you are observing the same phase every single day? Is that data really going to be enough to do whatever it is that you are doing? For example, in the eclipsing binary problem that you solved, remember that you really needed to measure the start and end of the eclipse very carefully, which means you need a lot of data around that point. And in fact, while simulating that data, that's exactly what we had done. We had given you lesser data points in the mid eclipse intervals as opposed to the eclipse itself. So we will do sanity checks like that. And then, for example, tonight we are actually observing a gamma ray burst, which is a very high priority target. So even if you had given me stuff tonight, we would not have observed it today. But once we have your request, then we will see, or if someone is doing the exoplanet, those exoplanet eclipses don't occur every day. So we will keep those things in mind and we'll use them in our scheduling. We'll get the data and then we'll give you a zip file containing a bunch of FITS files. After that, you have to go forward with analysis and everything, and then reports and presentations and things I'll tell you about in the end. Does that answer your question?
Yes, sir. And also for time series based observations, should we specify the exact time in the night in which we want to observe?
You can give preferences, but see, that is exactly the kind of stuff where we have to be in the loop. So if you tell me that I want my observations exactly at 12:01 tonight and then 5 a.m. In the morning and then exactly at this, that might not be very feasible. Okay, instead, when you define your problem and you put your rationale, you put down these things, make it a shared doc or whatever if you want, and then we will look at it and we will give you data that is sufficient to answer your question. Okay, if some of you ask for too many data points, we'll tell you itna le lo, itne mein ho jayega. If some of you ask for too few, we'll give you something else. We'll give you more data points. So we will look into those things. We will find, for instance, think of it this way. Okay, if you are observing a system which has a binary period of 3 hours, and you want observations spread over uniformly over the 3 hours, it really doesn't matter if I do it from 9 to 12 or 12 to 3. So those kind of things are important for us. Remember, we are actually using a research class telescope which is publishing a lot every day that it takes data for research. So we are putting aside all of that and making that telescope available for learning. So we can't be very rigid. There will be some cases, if you are again doing an exoplanet transit, then that will have a very specific set of time slots as a requirement for observations. But if that is not the case, so I'm not officially imposing a deadline of defining your targets before midsem, but I'm strongly encouraging it. That has two advantages. First is that it ensures that we can get your data set in good time. And second thing is it means that you actually have your data available as soon as midsem is over, so you get a longer amount of time to do the analysis for your project. If you wait until midsem is over, you give me your target on 5th of March, and then after that I put it in our observing queue. Next 2 nights might be something high priority. It gets observed starting on maybe 8th of March. You had requested observations for 5 days. So 12th 13th को observations खत्म होंगे. So देखते देखते you have lost half the month in something like that. So if you know what it is that you are doing, if you have picked your final target, even if you are still tied between, so if let's say 4 people in the group can't converge on one target, you have 2 targets in mind, sure, we will pick one of them, or we will help you identify why target X is better than target Y. Okay, so go ahead and make your requests as soon as you can.
Yes, sir. And also another question. So whatever image we will be getting, so like, will all the sources present in that image will be like fully solved in terms of the astrometry and photometry?
Yeah. Photometry is your responsibility. Astrometry we will do for you.
Okay, so like you will give us a FITS file in which the coordinates of each pixel will be there.
This is what would have been covered on Tuesday, but now will be covered post midsem. So yes, but you will know what the coordinate of each pixel is. And if you want to do single source, then we'll teach you how to do aperture photometry on single sources if you have crowded fields. Or if you want to automate it and want to do HR diagrams, then we'll point you to resources where those things can be done. All right, that's the end of our lecture slot. Any last questions before we close?
So what do we do for crowded fields? What did you say?
We'll tell you resources on how to go for.
Okay.
What I was essentially hinting at is that if you are trying to do something more advanced, then we won't cover it for the entire class, but we'll tell you where and how that can be done.
Okay, sir.
Okay, then. See you all in the midsem demo session on Tuesday, and all the best for your midsems. Bye.